Hello, we are Three Rivers Engineering. My name is Yuri, and I'm joined by Gavin, Jesus, Jamie, Miriam, and Chase. This presentation will discuss the background and overview of the Tijuana River pollution crisis, along with the proposed design to expand and improve the current treatment plant. We will also be discussing the use of water reuse to be used for landscape irrigation. The Tijuana River crosses international boundaries and flows from Tijuana, Mexico through San Diego, California. With a large population boom on both sides of the border, the current South Bay International Wastewater Treatment Plant is not able to keep up with the demand. The current treatment plant is able to treat up to 25 million gallons per day. There is currently a discussion in expanding the treatment plant as the treatment plant exceeds capacity during the rain events. Water reuse is also being explored to be used in landscape irrigation for Tijuana. The overall goals of the project include the expansion of wastewater treatment plant to be expanded to treat up to 75 million gallons of wastewater per day. An advanced water treatment plant will be built on site to directly treat wastewater up to standards and to be used for landscape irrigation. The water treatment train will also include reverse osmosis, UV disinfection, and an advanced oxidation system. Concerns for this project can include meeting requirements specified in Title 22. There is a certain log removal that is expected to be met. There also isn't a singular place that the wastewater comes from, with there being many different sources of wastewater that funnel down into the Tijuana River. There is also political issues. Since this project crosses borders, the federal government is involved and may pose an obstacle in fixing this issue.
For our nutrient removal, we selected the New Virginia Initiative Plant process. This process has lots of good implications for both nitrogen and phosphorus removal, which is important due to algae growth and other biological issues, as well as the state of California has regulations requiring less than 10 milligrams per liter of nitrogen for groundwater recharge. This design also only has a detention time of 90 minutes for all zones and has been known to have a lower BOD to phosphorus ratio needed in the wastewater to still be effective. This is ideal because during wet weather events, the wastewater can get diluted and it can be harder to treat.
Advanced purification is critical in turning wastewater into a safe, non-potable resource to be used for many tasks in groundwater recharging. This process is done through many steps. First one being membrane filtration to remove suspended solids and microorganisms, followed by reverse osmosis eliminating salts. Next comes UV disinfection, killing viruses, pathogens, and finally advanced oxidation processes. This all results in a high quality water ready for groundwater recharging and other non-potable uses. In order to accomplish the 20 million gallons a day we were setting out for, we would need 22.2 million gallons of wastewater to start. Membrane filtration was the first step. And membrane filtration, we decided to go with a cellulose acetate membrane that would be located outdoors as it would take up a lot of space. This membrane would take up This membrane would have a 2.5 log removal grade, removing approximately 99.68% of all contaminants. In order to meet our goal of 20 million gallons a day, we would need the 22.2 million gallons of wastewater, meaning that the total area of membrane needed would be 54,513 and a half square meters of membrane, being split across 16 skids with 76 modules in each, leading to a total of 1,012 modules.
For our reverse osmosis design, we selected a TFC or thin film composite membrane. For each of our stages, we had approximately 50 pressure vessels with a total of 14 stages in our design. If you look below, you can see we added 3 walkways for ease of access to all of the vessels, as well as stacking them 5 high and having 10 columns. The full 14 stage design you can see to the right. Initially, we had 5 stages. Secondarily, we have 5, and then the last 2 drop down to 2. This is all anticipating 220 million gallons per day of permeate, a 6 log removal of all solids, a rejection of 99.9999% of all solids, a recovery of 90%, which leads us to an influent of 22.22 million gallons per day. With that in mind, that's about 2.22 million gallons per day of retentate produced. This can either be recycled back into the treatment train to go through reverse osmosis again, or if the facility is operating at or above capacity, then the retentate can be sent to a storage tank where it can either be retreated later or disposed of.
For UV disinfection, we aim to achieve a 6-log removal of pathogens, which required a UV dose of 131.3 millijoules per square centimeter. Assuming our UV lamps have an intensity of 5 milliwatts per square centimeter, the necessary contact time was calculated to be 26.3 seconds. To treat 20 million gallons of water per day, we determined that 1,315 UV lamps would be needed, arranged into 263 banks with 5 lamps each. All of this would require about 352 square feet of space for the UV disinfection system.
The use of UV light is a common method for disinfecting water, but it does face limitations. Advanced oxidation is a technique that can be combined with UV light disinfection. By using advanced oxidation, it generates hydroxyl radicals, which is a highly reactive molecule that allows it to become a potent oxidizing agent. Advanced oxidation not only disinfects water, but it also provides a 6-log removal of microorganisms and a 0.5 log removal of 1,4-dioxane.
Now we'll be walking us through how we calculated the irrigation volumes and how much land in Tijuana can actually be irrigated using the 20 million gallons per day of recycled water. So we started by looking at the evapotranspiration rates and the precipitation. ET, which is evapotranspiration, measures how much water is lost through evaporation from the soil and transpiration from plants. By subtracting precipitation, we get the net irrigation requirement, which means it's basically how much additional water needs to be applied. Moving on, we had to adjust for the real world conditions. So in this case, it's Tijuana. So we had an irrigation efficiency of 80%, meaning 20% of the water applied is expected to be lost. We had a leaching requirement of 11%, which ensures the salts don't build up in the soil. And we had a landscape coefficient of 0.24, which is a combination of the vegetation, density, and the surrounding microclimate. So once we had all these adjustments, we calculated the monthly irrigation depth, which is also the hydraulic loading rate. We use a supply of 20 million gallons per day of recycled water, which comes out to about 27.6 million cubic meters per year. So we determined that this was around 87 hectares of landscape in Tijuana that could be irrigated annually.
For the Tijuana Water Reuse Project, we are using up to 20 million gallons per day of recycled water to irrigate around 8,700 hectares of urban and green areas. We calculated irrigation needs using evapotranspiration rates, local precipitation, and an 80% irrigation efficiency and an 11% leaching requirement. The landscape coefficient was 0.24 based on plant type, density, microclimate, and in terms of logistics, we estimated that the total space required for membrane filtration, reverse osmosis, and UV disinfection is about 7,222 square feet, and we have enough space west and south of the existing plant to build these units. The treated water will be pumped into underground aquifers using recharge wells, which helps with storage and prevents seawater intrusion. However, potable reuse is not currently allowed at the facility because it lacks the advanced treatment and source control systems required under the California Title 22 regulations.
Sustainability. Our design incorporates the 3 pillars of sustainability: environmental, economic, and social in the following ways. Environmental sustainability. It prevents pollution in the Tijuana River and Pacific Ocean through advanced wastewater treatment. It reduces nitrogen and phosphorus, protecting aquatic ecosystem and preventing harmful illegal blooms. It supports long-term water availability by recharging groundwater and preventing seawater intrusion. Economic sustainability reuses 20 million gallons per day of treated water for irrigation, cost-effective and resource efficient. Infrastructure upgrades are efficient and compliant, reducing future costs. Enhances local water resilience, reducing dependency on imported water. Social sustainability improves public health by reducing untreated sewage discharge, preventing beach closures. Ensures reliable access to reclaimed water in Tijuana communities. Promotes US-Mexico collaboration, supporting cross-border cooperation and social stability. This water reuse project supports multiple SDGs and their specific sub-goals, including SDG 6.3. The project improves water quality by reducing pollution and safely reusing treated wastewater. SDG 6.4. It increases water use efficiency by recycling wastewater for irrigation and groundwater recharge. And lastly, SDG 6.5, it supports integrated water management throughout the US-Mexico collaboration on shared water resources.